All right, let's take a look at this next example. We want to find two positive numbers with a product of 1600 whose sum is a minimum. So let's go through the steps. We've read the problem. We don't really need a picture on this one. Introduce some variables. So let's let the two positive numbers be x and y. And so that's our variables. The quantity to be minimized or maximized is q. I'm going to call it q this time, and it's the sum. We want x plus y, and we want that to be a minimum. Express q in terms of the other variables. Got that? If q is a function of more than one variable, eliminate all but one of them. Okay, on this one, q is x plus y. So we need to somehow get rid of one of those. Let's eliminate y. Now, we're told that the product is 1600. So xy is 1600. So that means y is 1600 over x. So that tells me that q is x plus 1600 over x. All right. Now find the maximum or minimum value of q. We're trying to find the minimum value, but that doesn't really affect how we go about finding it. In whatever case, we take the derivative and set it equal to 0. So let's see, q prime in this case, derivative of x is 1. Now, derivative of 1600 over x, I could write that out as 1600x to the minus 1. Take its derivative and you get this. So this is minus 1600 over x squared. And that's the thing that we're trying to, we're going to set that equal to 0 and solve. So let's see, I'm going to move this to the other side. And so you just get 1 equals 1600 over x squared. And so cross multiply, you get x squared is 1600, where x is plus or minus 40. Now they said that our x and y have to be positive numbers. So x equals 40 is my critical number. All right. Now, what are our limitations on 40? I'm sorry, on x. Well, it has to be positive. There's no upper limit on it, but realistically, if we're trying to keep the sum as a minimum, we don't want it to get too big. But anyway, let's look at this critical number and see if it gives us a minimum. I'm going to do that by plotting it on a real number line. So I'm going to put 40 here. You know, normally I would go from one end to the other. But since these have to be positive, instead of going all the way back on the real number line, I'm going to stop at 0. So let's pick two numbers to plug in. I'm going to plug in 1, and I'm going to plug in over here. I'm going to plug in 100. And we're going to see what that does to q prime, and in turn what that tells us about q. I'm going to slide this down a little bit. All right, so if I do q prime of 1, I'm plugging 1 back into this over here. So q prime of 1 is going to be 1 minus 1600, which is very negative. If I do q prime of 100, I get 1 minus 1600 over 100 squared. 1600 over 100 squared is small. It's less than 1 because that numerator is bigger than the denominator. I said that backwards. The denominator is bigger than the numerator. Anyway, this winds up being 1 minus something smaller than 1, so it's positive. So that tells us that q goes down and then goes up. So this 40, sure enough, is a minimum. So x equals 40 is a minimum. But they said find two positive numbers. So we get x is 40. And what about y? Well, come back over here. We know that y is 1600 over x. So x is 40 and y equals 40. And that's our answer. All right, let's look at the next problem. A farmer has 2,400 feet of fencing and he wants to fence off a rectangular area next to a river. That's supposed to say next, not nest. A rectangle next to a river. What dimensions will maximize the area? You might have seen these kind of problems when you took pre-calculus. And if you did those, you used a formula for the vertex. In this case, let's see, here's the river. It should have blue water in it. All right, and we're going to fence off an area like this. So here's our picture. I'm going to call this length x and this length x. And this length over here is going to be 2,400 minus 2x. Because basically you use x feet of fence here, x feet of fence here, and whatever's left is going to be 2,400 minus 2x. So let's see, we're trying to maximize area. So area is going to be 2,400 minus 2x times x. And if you multiply that out, you get 2,400x minus 2x squared. And we can take the derivative of that. So 2,400 minus 4x equals 0. So what do we get there? 2,400 equals 4x. So that gives me x is 600. So the dimensions that would maximize this would be 600 feet wide and 2,400 minus 2x, so that's 1,200 feet long. That's going to maximize my area. And I skipped over the part about proving that this was a maximum. I should go back and say something about that. How do we know it's a maximum? Well, there are two ways. You could come over here and say, here's my critical number of 600. And if I look at A prime on both sides of it, say over here A prime of 0 and over here A prime of 700. Let me write those below here. If you do A prime of 0, you're plugging 0 into here, so you get 2,400. And if you do A prime of 700, let's see, you get 2,400 minus 2,800, which is negative. So sure enough, you can see that the area is going up and then down. So sure enough, you get a maximum there. Now another way to tell you get a maximum here is by just looking at the original function. This is our area function. It's a parabola. And the fact that this has a negative coefficient on x squared, that means it's going to open downward and therefore it's going to have a maximum. So either way you get it, that's the answer there. All right, let's do the next example, example 4, in the next video.